Hi guys, today we're going to be learning about the characteristics of polynomial functions. So this is our first lesson in our unit on polynomials. All right, so our goal is to identify those key characteristics. So remember back to your good old Algebra 2 days when you talked about like minimums, maximums, end behaviors, x-intercepts, y-intercepts, all that good stuff. Well, that's what we're going to be talking about today. So this definition is given to you on your sheet. It says a polynomial function is a continuous function that ranges in degree. So we remember, or we should remember, the definition of continuous, right? So an unbroken curve, all right? So you don't have any holes or anything like that. So, and below it says is the equation for a polynomial to the nth degree. So whatever that highest power is your n. Okay, that's your degree. Remember, that's just the exponent that we're talking about when we're talking about degrees. All right, so let's talk about some of the polynomial functions that we already know and we know some stuff about. All right, so the first thing that we already know, or the first few that we already know. So if we have a constant, so f of x, remember f of x is the same as just saying kind of y equals, all right, because f of x is just saying the function value at x. So you plug in a number for x and you get out a y value. Okay, so don't let that throw you off. All right, but anyway, so think back to our good old piecewise days, right? When we had a constant function. So our degree here is 0 because there's actually no x there. Even if I put an x there, it would be x to the 0 power, and anything to the 0 power is 1. So our picture is going to look like this. All right, just a nice horizontal line. All right, well, if we're dealing with a linear function, is what the next one's called, that has a degree of 1, right? Because x is the first, and that's going to look like a nice diagonal line, right? We figure out our slope, rise over run. For the next one, f of x equals x squared, that's called a quadratic. The degree is 2, and the picture looks like a U shape. All right, and remember, that's also called a parabola. All right, cubic, f of x equals x cubed, has a degree of 3. And that kind of looks like what we call in Algebra 2, like disco dance, if you will. So it kind of looks like that. And then quartic is normally as high as we'll go. For the most part anyway, and that has a degree of 4. And its picture, interestingly enough, can look like a W. All right, or it could also still look like a U, and that's just kind of depending on a few things here that we're going to talk about. All right, so let's talk about end behavior and how to determine that. All right, so we can actually determine our end behavior without actually drawing a graph. Okay, now we could still graph it just to double check ourselves, but to figure out our end behavior, when we're determining it, we're going to first look at our leading coefficient. And so we look at it and is it positive or negative? All right, and you want to have your function with the highest exponent and then working its way down. So that tells you your leading coefficient. All right. And so that information, whether it's positive or negative, is going to talk to you about the right end behavior. And we'll talk about that more in just a moment. All right. Then you look at your degree, whether it's even or odd, for your left end behavior. So those are the two things that we look at. Okay, now end behavior, think back to your good old Algebra 2 days. So I'm going to go down a little bit on this blank space. All right, no matter what our function looks like, it could be crazy looking. All right, end behavior is talking about what your arrows are doing. Okay, so if I looked at this arrow right here on the left, all right, this is my left end behavior, right? So it's going to the left and it's also going down. So because it's going to the left forever, x is going to negative infinity. And because it's going down forever, your f of x or your y is going to negative infinity as well. Okay, that's what we mean by end behavior. So hopefully that rings some bells for you. And if not, we'll hopefully review it right now. All right, so there's this little handy chart here. All right, so if All right, your leading coefficient is positive. All right, and your uh, degree is even. That tells you two things, okay? So first of all, if it's positive on the right, you're going to be going up, okay? Um, if your degree is even, it's going to do the same thing on the left and on the right. So we think of this as up, up. Okay, so what that looks like is x goes to infinity, so this is the right hand behavior. F of x is also going to positive infinity. And as x goes to negative infinity, f of x is still, I'm sorry that that keeps moving around here. Undo that. All right, f of x is still going to positive infinity. It's up, up. All right. Now, what happens when that leading coefficient is positive, but our degree is odd? Well, for odd, think opposite. So because that leading coefficient is positive, we still are going to go up on the right, but because it's odd, odd opposite, it's going to be going down on the left. So that's as x goes to positive infinity, f of x is still going to go to positive infinity. But as x goes to negative infinity, stay put, little guy, f of x is going to go to negative infinity as well. All right. So an example of that would be your cubic function, right? Because it's going up on the right and down on the left. All right. So if our leading coefficient is negative, that means it's going to be going down on the right. But since it has an even degree, it's going to do the same on the left. So as x goes to infinity, f of x will be going to negative infinity. And it's going to repeat that on the left. So this is what we would call down, down. Sorry that that moved again. So this one, sorry, this one is the down, down. Okay, so you can think of like an upside down parabola, if you will. All right, and then for the last part, so what color have I not used? I haven't used red. I'll use that. So if your leading coefficient's negative, we know it's going down, right, on the right. But because your degree is odd, it's going to do the opposite on the left, so it'll be going up on the left. So x goes to infinity, f of x is going to negative infinity. And then as x goes to negative infinity, so talking about the left end behavior, f of x is actually going to positive infinity. So this is what a negative cubic function looks like. All right, so last few characteristics and then we'll do some practice. So here are some other key characteristics of polynomial functions to the nth degree. So remember, your degree is n. That's what we're referring to it as. So x-intercepts. A polynomial will have at most n x-intercepts. All right. So it could have at most n, it could have less than that. And the less than that talks about when we have complex solutions. So when we don't cross that x-axis. All right. Y-intercepts. This is where the function crosses, obviously, the y-axis. And so we're going to plug in x equals 0 into our function. So we're going to put 0 in for x, and then we see what's left over. And you'll notice that what's left over is just the constant. So the number. So like if I have x squared plus 3x plus 5, sorry, I should put f of x equals. All right, my x-intercept is just going to be 5 because, or sorry, y-intercept, because I plug in 0 for both of these and they go away. Okay, so that's an easy way to get your y-intercept. All right, so for zeros, roots, solutions, those are all synonyms of each other. A polynomial always has n zeros. All right, so this is where we take into account those complex solutions. So remember that x-intercepts and zeros root solutions are very similar to one another, right? X-intercepts are actual physical points, whereas zeros root solutions, you can have a solution that's not real or it's complex. And so you're not going to see it as an x-intercept. All right, and then relative extrema. So think back to your good old algebra 2 days. You might have heard them as turning points. It's where we're changing direction from like increasing to decreasing or decreasing to increasing, right? Also known as your minimums and your maximums. All right, and a polynomial can have n, or will have n minus 1 extrema. All right, so let's do some examples. Okay, so we've got f of x equals, well, you can see all that good stuff there, x cubed minus x squared minus 2x. This has a degree of 3, right? That's our highest exponent. The leading coefficient is 1. So my degree is odd, and my leading coefficient is positive. So I'm going to actually jump down and talk about end behavior. So because my leading coefficient is positive, I know that on the right, I'm going to be going up to positive infinity. But because my degree is odd, I know it's going to be doing the opposite on the left. So as x goes to negative infinity, f of x is going to be going to negative infinity. All right, my possible extrema, remember that's always your degree minus 1. So 3 minus 1 is 2. All right, my y-intercept is going to be my constant. Well, there's no constant. When I plug in 0 for all of these x's, everything goes away and I'm left with 0. So that's my y-intercept. It's going to be at 0, 0. Okay, and then my possible zeros, remember that's always n, so 3, there's 3 possible zeros. Now let's actually find them. So to find them, we are going to factor this. I'm going to erase so I can factor it. All right, so we can take out an x, and we're left with x squared minus x minus 2, all equal to 0. I don't care how you factor, but this should be an easy factoring. It should be x and x, 2 and 1. This is going to be minus, this is going to be a plus because we want to get out negative 1. Then we set each of those factors equal to 0, and this gives us our actual zeros. So if I set x equals 0, well, x equals 0. If I set x minus 2 equal to 0, I would add 2, and I get x equals 2. And then x plus 1 equals to 0 is x equals negative 1. All right, and if I wanted to kind of sketch a graph just without going to decimals or anything, I could, because here's 0, 0, here's 2, 0, here's negative 1, right? So I have all my x-intercepts. I know that on the right, I'm going to be going up, and on the left, I'm going to be going down, and then in between is just going to kind of be this like swirly twirly thing. So you see those two extrema there, a maximum and a minimum. Okay, example 2 is there. Feel free to try it on your own and press play whenever you're ready. The degree there should have been 4. The leading coefficient was negative 2. So those things tell me, well, because my leading coefficient is negative, that means on the right, I'm going to be going to negative infinity. But because my degree is even, that means on the left, I'm going to be doing the exact same thing, right? So it's also going to negative infinity. So this is a down, down, if you will. Possible extrema should be 3, because that's 4 minus 1. Again, my y-intercept happens to be at 0, 0 because there's no constant term. My possible number of zeros is 4. Okay, and then my actual zeros, remember we figured that by factoring. So I'm going to factor out a negative 2x squared. Remember to factor out a negative leading coefficient whenever you have a negative leading coefficient. Okay, and that's going to get me x squared minus 1. And then I can factor x squared minus 1 to x plus 1 and x minus 1. All right, so let's pause there for a moment. So now if we set each of those equal to 0, so negative 2x squared equals 0. Sorry, I accidentally wrote the x twice. I would divide by negative 2, still get 0, and square root 0, and you still get 0. Technically, when we square root, we get plus or minus. So technically, this is what we would call a double root because plus or minus 0, but it's just 0. I'll show you what I mean by that in a moment. If you set x plus 1 equal to 0, you get x equals negative 1. And if you set x minus 1 equal to 0, you get x equals positive 1. So what does this look like if we were to sketch it? So 0, negative 1, positive 1. We know it's going to end up being down, down, and then this is a double root. So it's going to kind of look like this where we just graze that 0 like that. We just hit it right at that bottom minimum right there. All right, so this last bit, I'm going to skip the U tries for now. This last bit is about Descartes' rule of signs. So with Descartes' rule of signs, we're going to use this rule to determine our number of possible positive zeros and possible negative zeros. We're not going to find the actual zeros, just figure out the possible. And really, this example should have an f of x equals in front for it to actually be a function. All right, so to find the number of possible positive solutions, we're going to look at the number of sign changes in that function f of x, and then we're going to count down by 2's. So you start with a positive. So I'm just rewriting the problem real quick. And again, I should put f of x out front. So this is positive minus 5x squared, so that's negative, positive, then negative. So you change from positive to negative, that's one change, two changes, three changes. So 3 sign changes. All right, so there could be 3, or counting down by 2's, 3 minus 2 is 1, or 1 positive solution. Solutions if it was 3. All right, to find the number of negative solutions, we look at the sign changes for when it's f of negative x. So we're going to plug in negative x into our function. So it's going to be 3 times negative x cubed minus 5 times negative x squared plus 6 times negative x minus 4. So negative x cubed is negative x, so it's going to be negative 3x cubed. Right? Negative x squared is positive x squared times negative 5 is negative 5x squared. It's going to be 6 times negative x, that's negative 6x, and then a minus 4. Now you should notice it goes from negative to negative to negative to negative. There's no change. There's no sign change. So that means there are no negative solutions. And that's it.